Okay, these are some basic notes on section 7.3, and we're going to talk about finding solids by revolving a curve about the x or the y axis, or some line parallel to the x and y axis. And again, to find volumes of a solid revolution. These are solids of revolution, and we've got two different methods we're talking about first, the disk method and then the washer method, and then we'll talk about known cross sections. That's the third technique that we cover in this section. And the disk method is basically if we're going to revolve something about the axis, then what we'll do is we'll think of it, and here's kind of an example. We'll be going over this example, but just to illustrate some of the formulas. If we have this curve here, y equals the square root of x, and we're going to revolve it around the x-axis. Okay, then it forms a solid. It's like kind of the nose cone of a rocket. And we can divide this, and we can think of finding the areas by using cylinders. And we did some nose cone problems earlier when we were using approximations, I think back in chapter 5, and we used cylinders. Remember, I think we only used about 4 or 5 cylinders. I think 5 cylinders to estimate the volume of a nose cone. So we're doing the same thing, except now that these little cylinders are going to get thinner and thinner and thinner. Now, remember, the volume for a cylinder is base area times height. The base area is a circle. All right? So if we take the volume, if we want to find the volume of each of these little cylindrical discs, all right, that will be the base area, which will be the circle, times the height, which will be the thickness, and the height in this case will be the delta x. So we're going to sum up all these to find the volume, and we're going to sum up all these little cylinders on this interval a to b. And this is how we get our basic disk method formula. Volume equals the integral from a to b of the area of the disk, which is the area of a circle, times the thickness, which is going to be the dx. That's the delta x, the dx. All right. And again, the area of a cylinder, the base area is, that's our base area is a circle. So there you go. So that's your disk method. So let's take a look at some examples. And again, we'll be using these forms. Okay, now this is with respect to x. It can also be with respect to y. And we'll see some examples for that. And the other method is the washer method, and we'll talk about that. But that's where basically we have a kind of a hole in the solid, kind of like a cylindrical hole. It could be a cutout. And what we're going to do basically is take the large volume, the volume of the whole thing, and minus the volume of the interior or whatever we're taking out. And that's going to give us the total volume. And this is what we call the washer method, because instead of discs, we have washers. And we'll see those in just a second. So let's look at some examples here. So again, find the volume of the solid form when f of x, which equals the square root of x, in this case, is revolved around the x-axis. So there's our good old John Travolta curve. And it's going to be from 1 to 4. So basically, again, the volume is just the base area, the area. Area is a function of x. Now the area of a circle is just pi r squared. And what's my r? Well, my r is going to be whatever this y is. Okay, so again, I'm using this formula here. And I'm going from 1 to 4, so my a and b are 1 to 4. And my radius is just going to be, again, this is the value of this, which is just going to be y, which is just going to be the square root of x, so that's my radius. So that's real easy. So pi times radius squared, and then the square root of x squared is just x, so I take the antiderivative of that to evaluate that using the fundamental theorem of calculus. I can do it like that. I can take the pi out in front, and I'm going to evaluate, or I can leave it in this case I left it as a coefficient. So that's x squared over 2, that's the antiderivative, and I evaluate that from 1 to 4. And in this case, then I factored out the pi. And at 4, I've got 4 squared, which is 16 over 2, minus 1 squared over 2. So that's 16 halves minus 1 half, which is 15 halves times pi. So there was your answer. Okay. So not too difficult. This method. Let's take a look at another example. Example 2. Got lots of examples on this section. Okay. I'll find the volume of the solid form when the function or the curve f of x equals the square root of the sine of x is revolved about the x-axis on the interval from 0 to pi. So again, we've got our volume equals area times dx, and that's going to be pi r squared. Now if I look at this, this kind of is what the sine curve looks like, the square root of the sine of x. And remember that the key points are going to be the same, because the square root of 1, the sine of pi over 2 is 1, and the square root of 1 is 1. And the sine of pi is 0, and the square root of 0 is 0. So it's going to look, basically have the same endpoints. And this is kind of a representative little disk. It's going to draw these. And you can see the radius of this disk is just going to be the value of the function, so it's just going to be the square root of the sine of x. So I just put this in the same formula we used before. Volume equals pi times radius squared dx, because that's my area. And these are going to be the areas of each of these little disks, and this actually represents the height. We're going to take that integral and sum them up, and add an infinite number of these actually. And we end up with, and I took the pi out and put it in front, so the integral of sine of x from 0 to pi dx. And the antiderivative of the sine of x is negative cosine of x, so I'm going to evaluate that from 0 to pi multiplied by pi, so pi. And again, this is negative cosine of x, so I evaluate that at pi, and I evaluate that at 0. And we have a negative also actually on the cosine, and then a negative from this application of the fundamental theorem of calculus, f of b minus f of a. And the cosine of pi is negative 1, so I got negative 1, and the cosine of 0 is 1, but I got negative is positive 1, and this ends up being 2 pi. Okay, so that's example 2. And we'll do a few more.